Okay, let's talk about ideal gas processes. An ideal gas process is a process that you do with an ideal gas, expanding it, contracting it. There are lots of different ones. When I think about an ideal gas process, I think about a can that has a gas in it under a top that can slide up or down. That top is called a piston. That allows me to change the volume of the gas. When I change the volume of the gas, the temperature may or may not change, as we know from the ideal gas law. Ideal gas processes can be illustrated with lines on a PV diagram, as shown here. So we can think of the starting state or the initial state as being 0.1, where the volume's about 1 cubic meter and the pressure is about 7.5 kilopascals. And we can think about the final state as being 0.3, where the volume's 2 cubic meters and the pressure is 2.5 kilopascals. And we can change the pressure and the volume from those initial values to their final values in an infinite number of ways. Two different ways are illustrated here with the two paths. One thing that we'll need to do is to calculate temperatures. We can do that, of course, using the ideal gas law. PV is equal to nRT. We can know P and V from the PV diagram. N is given to us. That leaves us one equation and one unknown, T. And so we can calculate the temperature at different points as illustrated in this diagram here. So as I said, there's an infinite number of paths that connect any two dots or states illustrated on a PV diagram. We do want to think a little bit about what those abstract lines mean, because they mean something about the real world. So if I want to expand a gas, if I want to have its volume increase, I can do that by taking the piston, that's the slidey top, and slowly moving it to the right, in this case, as you see in part A of this diagram. On the other hand, instead of having a slidey top, I could just have a membrane, like a piece of rubber or something, and it could suddenly break. In both cases, the volume of the gas is going to increase. Those are both expansions. But the first one is called quasi-static because at all times the pressure and the volume and the temperature are well defined. They have one specific value. Whereas in the second situation, B, that is not the case. We will limit our discussion to quasi-static processes. I have a before and an after. The volumes would be the same. That's indicated in my picture here. And I know that the pressure is bigger in the after picture. So I know that the temperature is bigger in the after picture as well. Because as I said earlier, the pressure is some constant, positive constant times the temperature. Now we want to think of what ideas should we use to solve this problem. Well, we only need to use the ideal gas law. So we know that PV is equal to nRT. All right. Now what we'll do is we'll say, all right, PV equals nRT, but N and R are constant. So P1V1 over T1 is equal to P2V2 over T2 because each one of those is equal to nR. And then V2 is equal to V1. So we can divide both sides by that. And then we can solve for T2. We get the expression you see here. T2 is equal to T1, V2 over V1, P2 over P1. To go to the next equals, well, we use the idea that V2 is equal to V1. Then we have an expression. T2 is equal to T1 times P2 over P1. We know all those numbers, so it's time to plug in. We plug in, we check our units, the kilopascals cancel, leaving us an answer in Kelvin. It's 318.9 Kelvin, and then we can convert that to Celsius. Okay, it's 45.75 degrees Celsius.